let's share. All right. How's everybody? Are you done with the homework? Homework 2 finished. Kind of. Where are you in the homework? Halfway through. Have you done the week form part? Say yes. Okay. I'm a little bit behind. I'm one lecture behind because of that one lecture that I spent doing Gauss quadrature. So this was supposed to be Monday, but we'll do it today. Just continuing with the finite element solution in 1D. A little bit of an announcement. I'm not here on Friday, so I will connect over Zoom for the Python lab. We'll still have it, but I won't show up here. I will just connect on Zoom. Just that one, and then I guess homework 2 is due on Friday. That's it. Those are the announcements. So let's get to it. Again, what we're doing on Monday was finally completing the whole thing, which is we have a strong form to weak form. That's the first 2 problems of your homework 2. We have doing approximation of functions, which is also problem 3, and probably problem 4 of your homework. And then what we are doing this week, which is not part of your homework, is how do we take the discretization with the shape functions, put that into the weak form, and how does that give us a system of equations? That's the whole goal. Basically, we want to end up with something that looks like this: KD equals F, so that we can solve it just like we were solving for the trusses. That's the point. Just a reminder, what does the weak form look like? The weak form looks like that. Find U such that it's in C0, so it's continuous, and it satisfies the essential boundary conditions. And then this integral equation is satisfied for all W's such that W's are continuous and they vanish at the essential boundary conditions. That's basically it. And then that's the general definition of the weak form. And what we were saying even last week when we were introducing the shape functions is that how do we build these U functions? How do we build these derivative functions? How do we build these W functions? What makes sense? And so the intuition here is to have a very modular way of defining the functions, where you have some functions that you never change. These are the shape functions. And then the way you construct the U functions or the W functions is just by moving some numbers. These dials that basically allow you to interpolate the functions. But the things that are the functions are the same. The only thing that you move is these numbers. What does the interpolation look like? In the book, you will see this notation of n times d. But as I was writing last time, this is equivalent to the way I was writing it in, if you don't write it in the vector notation, this is just the sum of the shape functions times the nodal values. Same for the W's. This is just the sum of the shape functions times the nodal values. And then derivatives is just the sum of the derivatives of the shape functions times the nodal values. Actually, it should be I underneath. Right? But this is the interpolation that we were introducing before. It's just a matrix notation that the book uses. Yeah, all right. So what we did last time, I'm gonna redo a little bit of it. But what we did last time is that if you grab that sum of shape functions times nodal values and you put it into the weak form, the things that are functions should stay inside of the integral, but this wi and this ui, those are not functions, they are just numbers. So you can take them out of the integral. And what you end up with is that all the w's are pushed outside of the integral, all the d's or the ui's are pushed outside of the integral. And what you're left with is a matrix that we wrote last time. I'll rewrite it now. That is the stiffness matrix. And for the force vector, again, you take the w's out of the integral, and what you are left with is just the shape function times that weighting function, the source term, or the body force. And that is our force vector. And then what I didn't do last time, this is when I ran out of time, is I didn't define this last term, this boundary force. But yes, so question up to this point of the general idea of what we are doing. Okay, I'll redo a little bit of what I was doing last time, which was just to recap exactly how I did it. How do you get this stiffness matrix? Again, one of the terms in the weak form is this du dx, well, with AE, right? So AE du dx, dw dx, d omega e. That was one term of the weak form. And then what I said is, what is the u dx? It's the sum of the derivatives of the shape functions times the nodal values. So this one ended up being, when we use the discretization with finite elements, this is just sum of dni dx ui. Let me use j for this one because over I, and sum over j of dn, sorry, sum over I dx wi. So again, nothing done here except that I'm using the fact that to represent the function is going to be the sum of these derivatives of the shape functions times the nodal values. And then what I said is that because these u, j, and wi are just numbers, I can just take them out. This is just algebra. And I end up with this. Just algebra there, and this defines a matrix that is the stiffness matrix of the element. And you can see that what is the size of this matrix depends on how many nodes you have per element. So for the linear elements, you have 2 nodes, so you have 4 combinations of I and j. You have, 1, 1, 1, 2, 2, 1, 2, 2. If you have a quadratic element, then you have 3 nodes, then you have 3 by 3 options, right? You can have 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, and 3, 1, 3, 2, 3, 3. So depending on which element you're using, the size of the KE. This is nice because this is a general definition, and the size will depend on how many shape functions you have, but that is always true. So this is always true. Actual KE computation depends on which element we are using. So if you do linear, then KE is 2 by 2 because you have 2 shape functions, so you have 4 combinations. If it's quadratic, then KE is going to be 3 by 3 because you have 3 nodes, 3 shape functions, so 9 combinations, and so on. And so for linear, then what does that KE look like? All we need to do is write out all the 4 combinations. So this AE dn1 dx, dn1 dx, then AE dn1 dx, dn2 dx. This one is AE dn2 dn1. And then dn2 dn2. this is our 2 by 2 stiffness matrix for the linear case. And I mean, there's some integral that you need to do. In some cases, you can do it analytically. In some cases, you do it numerically. I don't know if I put some numerical integration as part of your homework. Maybe, I think I did. For the linear case, you can do it analytically because the derivatives of the shape functions are just numbers. So the shape functions are linear, the derivatives are just numbers. So for linear case, actually, you can do the integral analytically. For linear shape functions, for example, dn1 dx is just minus 1 over the length of the element. dn2 dx is just 1 over the length of the element. You can work it out, but the first shape function is, I forgot, but x minus x2 over x1 minus x2. If you take the derivative, you get just 1 over x1 minus x2, which is minus 1 over the length of the element. So these are just constant. So the integral is trivial in this case. It's just AE 1 over L squared integral of dx, which is just the length of the element. So you end up with you can take out the AE because it's just a constant. So you can take that out, and then the dn1 dx over dn1 dx is just 1 over length square, and then you can take that out as well. And the integral that you are left with, I'll just do it here. You are basically just left with this. So for the linear case, you actually don't need to do any integral because this is just the integral of dx over omega e. Omega e is from x1 to x2. It's just the length of the element. Actually, this ends up being minus. Because of this minus here, you end up with, in the first one, minus times minus, you get plus, but in the other off diagonals, you get minus. So the stiffness matrix is just at the end. This is what I ended up last time with. AE over LE times 1 minus 1 minus 1, 1. So it's just like the truss element, but we got to that truss element stiffness the long way, but in a more general way. So if you look at this definition that I have right here, that one works for the linear element, but it will work for the quadratic element, cubic element, whatever it is. Not only that, but this structure will generalize to 2D, will generalize to 3D. We won't do 3D in this class, but it generalizes pretty well. And it also generalizes pretty well to not just the stress analysis problems, but the heat transfer problem. It will have basically the exact same structure. So even though at the end, for the linear case, we end up with just the truss element, the path that we took to get here is a lot more general. So it really works for all sorts of PDEs, and it will extend beyond 1 dimension to 2 or 3 dimensions. That's for the stiffness matrix. Any questions about this? Okay, so For the other term in the weak form, which was the force vector, in the weak form, it looks like W times some function, which is the body force, could be gravity. It looks something like that. And again, what we are going to do is we're going to replace that W with sum of shape functions times nodal values. So I'm going to replace this with sum of the shape functions times the nodal values. The B, I'm going to leave like it is. And then just like before, I'm just going to rearrange this. I'm just going to take the numbers outside. And then I'm going to end up with just the shape functions times Bx. And this is the force vector. And again, this definition is general for linear, quadratic, etc. It's just the integral of the shape functions times the body force. What is the size? Well, it depends on that I. So if you have a linear element, there's only two shape functions. So the I can take values 1, 2. So it's going to be a 2 by 1 vector. If you have quadratic elements, then I can take values 1, 2, or 3. So it's a 3 by 1 vector, and so on. So for linear, the force vector is just going to be that integral of either n1 of x times bx or integral of n2 of x times bx. Now here, I cannot really simplify it because it depends on what b of x is. So if b of x is a number, if it's just, for example, gravity, then it's easy because then I can take that outside of the integral and I just need to integrate the value of the shape function. Or if b of x is linear over the element, I can also figure out, and actually I think I have it later on. So in general, this is not simplifiable because I don't know what bx is. Simplifiable depending on b of x. So for example, let's say that b of x is just a number. Let's say that b of x is just some number. In that case, the force vector, I can just take that b naught out. And then what I'm left with is the integral of n1 and the integral of n2. Anybody want to guess what those integrals are? What is the integral of n1 over the element, and what is the integral of n2 over the element for the linear case? So remember that n1 is this line that goes from 1 to 0.
Slope.
It's not the slope, because the slope is 1 over the length. But just n1 looks like this from x1 to x2, and n2 looks like this. This is the second function. Looks like 0 to 1. This is 1. This is 0. So what is the area on the n1? Yep. So this is length over 2, length over 2. So that would be, but again, this is not simplifiable in general, depending on what b of x is. If the b of x is just a constant, then the force vector is just that value times length over 2, length over 2. I think I have also the case where b is linear. Well, I won't derive it, but I think it's on the slides. Any questions up to this point? It's a little bit of a recap of Monday. I'll upload the slides as always. All right. This is this is just repeating this is the derivation in the book. You can see that for the linear case, you end up with just AE over length times 1 minus 1 minus 1, 1. I won't go over this. I just did it. And then for the force vector, this is what the force vector looks like if B is linear. So this is another derivation that I don't want to do. So this one is force vector if B of X is linear and it goes from B1 to B2. So the one that I was deriving above was if B was constant. So I just assume the value was B naught. Then you get B naught times length over 2 times length over 2. If the B is not constant, but it changes linearly over the element, then you can plug that in and then do the algebra. And then this is what you end up with. You can see that if you plug in B0 here for B1 and B2, you get length over 2, length over 2. So those are simpler to get. Obviously, the B, like I said, is not restricted to be constant or linear. The B could be anything. In most practical scenarios, you can assume that the B is either constant or linear. So typically, you really don't need to integrate the force vector for the linear element. You will just go with either this one or the constant one. Yes. Just x2 minus x1 for an element, yeah. Basically the end of the element minus the beginning of the element. So for the interval before, that should have been like. Yeah, the area is length times 1 over 2 because it's a triangle. Yes. For the shape functions. Yeah. All right. So there's one example. Before I get to this example, which I do want to solve, let me do the one thing that I didn't do last time, which is I did a little bit the assembly. So right now I've defined the stiffness matrix and the force vector for an element. And there's the question that, okay, you can do this stiffness and force vectors per element, then you need to assemble it to the global system. And that one I had some mesh, maybe it's easier to do in an example, but let's say that you have, for a given element, you have some stiffness matrix, and then you have the values of the nodes that make up this element. So these are nodes that make up element. This is exactly the same that I did for the trusses. So then you will be able to assemble into the big K, right? So all you need to look for is where is that A and where is that B? And then maybe this is not exactly like this, something like that, right? So that you do like this term will go here. This term will go here. And these two terms will go here. So that's just the same that we were doing for the trusses. So for the assembly, you have your element stiffness, you write down the global known numbers, and you use that to map to the big K. So the size of this one is number of nodes times number of nodes. Similarly, for the force vector, your force vector for the linear case is just two elements, two nodes. So you have A and B. The global force vector will be the size n node. And then you just need to find where this goes. And then just add it up there. So the assembly is pretty much the same as we did for the trusses. I think I did that also on Monday. So what happens when you assemble the whole thing? After assembly, you're gonna end up with something that looks like this. Here are gonna be all the W's. Then here's gonna be the big K. Open a parenthesis. Here's gonna be the vector with the U's. So this is U1, U2, etc. And here's gonna be the force vector. And this has to be 0. And this is basically, this is also called the discrete weak form. And this has to be 0 for all W's such that W equals 0 at boundary with essential boundary condition or DHL boundary condition. So to remind you a little bit of I mentioned this when I was introducing the strong form to weak form. What is every one of these rows? So what is this, the first row, like this times this times this times W1? Do you remember what that is? What is the meaning of that first row and second row and so on? So to remind you a little bit of what the intuition behind this discrete weak form. So how does this connect to weak form and to strong form? So if you remember originally, we have the PDE, right? So we have the second derivative of U, actually something like this. So we have that equals 0 for the entire domain, right? 0 to 1, for example, with some boundary conditions like W of, not W, U of 0 equals something, and then du, I think this was U of 1 equals something, and du dx at 0 equals something. That was the strong form, right? And what I said that we were doing with the weak form was that we were multiplying that PDE by this weight function and integrating, and that was giving us, so when we did the weak form, essentially what we were trying to do was, this was the PDE, and then we wanted, instead of saying, I want to make sure that the PDE goes to 0 everywhere, what we were saying was, let me multiply by a weight function, let's call this W1, and then integrate the PDE just over that area. So it's kind of, when you multiply W1 by the PDE, you're calculating an average error. So when we were doing that, we were calculating an average error of the PDE over the region specified by W1. That was the meaning behind the multiply by the weight function and integrate, is that instead of caring about pointwise error, so instead of saying I need this PDE to be 0 everywhere, what I'm saying is, in this little chunk defined by W1, I want my average error to be 0. And so what we're doing with the FE is we're introducing a systematic way of defining these W's with the shape functions. So we have W1, we have W2, we have W3, and so on. So here, every one of these rows is one of those equations. Every one of those rows is, I want the average error over the space defined by W1 to be 0. I want the error over the little chunk defined by W2 to be 0. I want the average error over the chunk defined by W3 to be 0, and so on. That's the intuition behind this discrete weak form. When does this go to the strong form? Well, in the limit that I shrink my W's more and more and more and make them sharper, then I'm dividing my domain into finer and finer elements. Obviously, I get more and more equations. So in the limit, when I shrink this to just a tiny, tiny, tiny sliver, so it goes to infinity, then I recover the strong form. Well, obviously, I get infinitely many equations, which I cannot solve. But so as I mentioned when introducing the weak form, this gives you more flexibility because you get to choose basically how much do you care about your error by introducing that discretization with the weight functions. But that's what it's saying. It's basically saying each one of these says, for every choice of W, I want my average error to be 0. There's one thing that I haven't introduced. Why do we do the vanishing of the shape functions? Because for those, I actually don't know the force. So I need, for this product to be 0, in this force vector, I know all the forces, including the boundary terms, which I haven't added, except for when I don't know the boundary forces. So what happens when you know U? Let's say that you know, maybe I should do that. Actually, let me amend this a little bit. So these are the body forces, and let me also add the boundary terms. Right? So here I'm forgetting the boundary terms. The forces at the boundary. I mean, out of all those nodes, if it's just a 1D case, then there's just 2 that are on the boundary, right? So in this case, there must be 2 nodes on the boundary. and we either know the displacement or we know the force, right? In this particular example, there was one node for which we know the displacement and we don't know the force, and there's one node, maybe let me grab that as red. So there's one node for which I know the displacement, it's on the boundary. So this is the boundary node for which I know the displacement, but I don't know the force. There's an unknown reaction there. And there's another boundary for which, let's just say some U8, for which I know the force in the boundary. This one, there's a reaction that I don't know. So this is where the boundary conditions come into play. So this is one node on the boundary. With known force, I just added. But there's one node on the boundary with known displacement. So this is node on boundary. With known displacement. But unknown force. So this is the reason for the W to be 0, because I still want this equation to be 0, right? So I still want that line to be 0, but I don't know the force. How do I guarantee that that line is 0? I make the W corresponding to that boundary to be 0. So this is the condition of the W has to vanish at nodes with known displacement but unknown force, because I still want the equation to be satisfied. So therefore, this one has to be 0. That way I satisfy even that equation where I don't know the reaction. Aside of that, all the W's can be whatever. So all of the W's can be anything. So if I have that W times KU plus F equals 0 for all W's, except that one that has to be 0, then the system of equations is I don't need to care about W really. All I need is the K times U minus F minus the boundary terms. And the boundary terms, like I said, it's really just 0, 0, 0, 0, then there's a reaction, and then 0, 0, 0, and there's a force at the boundary. So in the end, the W's, you don't need to solve for the W's because W's can be anything. They are really just there to split the system into all of these equations. You can rearrange this if you want everything to appear on the right-hand side. So you can rearrange to have K times U equals the force vector plus the force vector on the boundary I just move things to the right-hand side. And again, remember that there's, in these boundary terms, there's going to be just zeros, except for the node in the 1D case, for the node that has the unknown reaction and the node that has the known force in the boundary. And obviously, for that unknown reaction, there is a known displacement. For this known force, there's still all the other ones are unknown in terms of the use. Any questions? So this is really just the same as the truss. So again, you have element stiffness, element force vector, assemble into the global system, take care of boundary terms. But aside of that, the setup is the same. Ku equals force. I made a mistake. This should be here. How do you solve this? Exactly the same as with the trusses. You either replace one of the equations with a trivial equation, or you do the split the system into the subsystems. So exact same as the either replace one equation by some trivial equation, or you split the system into subsystems, just like homework 1. Questions? Yes.
You're saying like WS can be anything. Does it still have to be like one that's each node?
You can pick one, and if you pick one, then it's exactly this. But you don't have to. So yeah, I mean, it can be whatever. So you can pick one and then all the ones zeros, and then you get the first equation and so on.
So you basically multiply that at the end.
So yeah, so that's why you don't care about it. You want the W times this thing to be 0. So then at the end, because the W's can be whatever, you can imagine that the way I described it here, that each of the W's represents one equation. That is basically, if you set one of the W's to 1 and all the other ones to 0, that isolates that first equation. And then if you do 0, 1, 0, 0, 0, that isolates the second equation. But you want all of them to be true. So it's basically you can take all these combinations of 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, etc. And that will give you all the separate equations. Or you can just say, ignore the W and just write out whatever, so multiplying the W. Any other question? Yes. No, because that one, the condition on the W is just that it's 0 whenever we know the displacement. And the only reason for that is that we don't know a force. So here, the only reason why I said W2 to 0 is because I want that equation to be 0, but I don't know the reaction. So I just force the W to be 0 so that I get that equation to 0. But in the other one, in the other boundary, for this FB, for that one, I know the force, and I need to solve for the displacement. That one is like a regular node, so I don't need to do anything with the W. So just for the nodes that have known displacement on the boundary, but an unknown reaction. All right. Well, I don't have time to solve this by myself, but I'll just, this is, I think this is a heat transfer problem, but you can see that it looks exactly the same. The weak form has the same terms. So if you follow the exact same approach, I mean, it looks exactly the same, just replace T with U. What does the force vector look like and the stiffness matrix look like for the heat transfer problem? They look exactly the same. There's really no change. Like this looks exactly the same. And the only thing that I want to point out before we leave is, I mean, the assembly for this problem is the same as for the trusses. You know, once you have the element stiffness, then the assembly is exactly the same. So if you have done it for the trusses, this looks pretty much the same. The body force, like I said, is the integral of the shape functions times the S. I think the S in this case is constant, yes. So then you only get basically L/2 times the value of the source term, because in this case the S was constant. So obviously there's two force vectors, and you do the assembly exactly the same as for the trusses. Then there's the boundary terms. The boundary terms, this first element does not have boundary terms. The second element actually had a boundary term, the boundary flux. So what does the global system look like for that problem? It looks like the stiffness matrix times the, I know we need to go. So this is the force from the source. This is the force from the boundary. It's split into two, but you can see that, you know, this looks just like the truss element. Maybe the only difference is that you get a force vector from, you know, source terms or body forces, in addition to getting the force vectors from boundary terms. And it's either a known force or an unknown reaction. All right, I'll see you on Friday on Zoom.